Trigonometry, Chapter 3, Radian Measure in the Unit Circle, Section 3, the Unit Circle and Circular Functions, Video 4, Evaluating Circular Trig Functions on the Unit Circle. The series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous videos, we completed the unit circle and defined circular trig functions. From this perspective, the input of the functions was an arc length on the unit circle, and the output were the ratios we've seen before for all 6 trig functions. In this video, we apply the circular trig functions to the unit circle. To apply the circular trig functions to arcs on the unit circle, we need to know the arc length associated with each point on the unit circle. Now, since we know the angle measures for each such central angle, such as this 30 degrees, the radian equivalent of the central angles match the corresponding arc lengths. Remember, r is equal to 1. So on the unit circle, the arc length s is equal to r times theta. That's the arc length formula. But since r is equal to 1, that's equal to theta. That simply means that the desired arc length is the central angle measure in radians. For example, the arc from 1, 0 to square root of 3 over 2, 1/2 has an associated angle of 30 degrees. The radian equivalent of 30 degrees is pi over 6. This means at the point square root of 3 over 2, 1/2, the arc length is s equals pi over 6. Similarly, the arc length associated with any other point on the unit circle equals the radian measure of the corresponding central angle. We include that in our unit circle diagram, the radian measures. To declutter the picture, we remove all the radii. And here's our complete unit circle. Each point, such as square root of 3 over 2, 1/2, has an associated ordered pair, arc length in blue, pi over 6, and central angle measure, 30 degrees. Now that we have the complete unit circle, evaluating trig functions is straightforward. Just remember, for any arc s on the unit circle, cosine of s is equal to x, sine of s is equal to y. For example, calculate the 6 circular trig functions of pi over 6. Well, at pi over 6, we have x equals the square root of 3 over 2 and y equals 1/2. Thus, cosine of pi over 6 is equal to the x-coordinate, which is square root of 3 over 2. Sine of pi over 6 equals the y-coordinate, which is 1/2. And tangent of pi over 6 equals y over x. So we would put the 1/2 over the square root of 3 over 2. But if we reciprocate the denominator and multiply, the 2's cancel, leaving us with 1 over the square root of 3, which becomes square root of 3 over 3 upon rationalizing its denominator. I would use reciprocal functions to get the remaining functions, reciprocal identities to get the remaining functions. So for secant, I would take the reciprocal of cosine after rationalizing its denominator. Secant of pi over 6 is 2 square root of 3 over 3. For cosecant, I would reciprocate sine and get 2. And for cotangent, I would reciprocate tangent and get 3 over the square root of 3, which, upon rationalizing its denominator, simplifies to just the square root of 3. With practice, using the unit circle to evaluate trig functions becomes quick, especially for sine and cosine. This, of course, is assuming that you are familiar with the unit circle, so get familiar with it. Now you try. Pause the video and try the following. Use the unit circle to evaluate the following. If you need to go back and rewrite it or take notes on it, do it. But find the value of these 3 trig functions based on the unit circle. All right, fair warning, if you haven't paused the video yet, solutions in 3, 2, and 1. I do want to point out that cosecant of pi was undefined because at pi was the point -1, 0, but cosecant is 1 over y. The y is equal to 0, so it's still possible for some of these functions to be undefined if their denominator contains x or y at the wrong time.